Welcome to the Math Record. Today we'll be starting to cover the graphical aspects of derivatives. This video will cover part 7 of chapter 2. However, we'll be splitting up part 7 into two videos. The first will cover maximum and minimums and increasing and decreasing intervals. In the next video, we'll be covering concavity and inflection points. Okay, let's begin. Let's start with maximums and minimums. So maxes and mins. There are two types of them. There is the local, which is referred to as the relative, and there is the global, which is referred to also as the absolute. So the general idea is that if you any single max or min is going to be a local, and if it's the highest value, then it's going to be the global max, and if it's the smallest value, it's going to be a global min. So that's basically the general idea of how it works. So how do you find the maxes and mins of a graph? Well, basically, all you're going to have to be looking for is that you have to find the x-intercepts of the derivatives. So let's give an example. Let's say we have an equation f of x, right? And we say f of x is equal to 2x to the power of 3 minus 9x squared and plus 12x and let's say plus a 6, right? And let's say this goes from, and it's restricted in the domain from -2 to 5, okay? So the x value only goes from -2 to 5. So it's like -2, -1, 0, like 1.5, 2.5, 3.14, 15, etc. So basically only the points between -2 and 5 exist. So how do we find the maximum and minimums? All you have to do is that you have to take the derivative of this. So what's the derivative of f of x? Well, the derivative. So the derivative of 2x to the power 3 is just 6x squared, right? Bring the exponent down and then minus 1. So 3 times 2 is 6. X, 3 minus 1 is 2. Okay. The derivative of 9x squared, bring the exponent down. So 2 times 9 is 18. X, 2 minus 1 is 1. Okay, so we just keep it like this. Derivative of 12x, bring the exponent down. So 12 times 1 is 12. And x, the 1 right here, right? The 1 minus 1 is 0. So x to the power 0 is just 1. Okay? So it's just 12. So what, and I'll just write this a little neater. So that's plus, and that's 12. Okay? So the derivative of a constant is always going to be 0. So the derivative of 6 is 0. So we need to find the zeros of here. So let's factor this out by 6x squared minus 3x plus 2. And you go factor this to 6x minus 1 and x minus 2. Okay? So this is our factor form. So our maximum and minimums are at x is equal to 1 and x is equal to 2. So how do we know if it's going to be a max or a min? Well, all you have to do is that you have to plug it into the original equation. So let's kind of delete this because we already know it's x is equal to 1 and 2 and I need space. So this one was x is equal to 1 and x is equal to 2. So technically, we have 4 points. So how do we have 4? We only have x equals 1 and x equals 2. Well, the boundary points also works too. So you have -2 and 5 also. So you have to put in x is equal to -2, x is equal to 1, x is equal to 2, right? And x is equal to 5. So you have these 4 points. Always remember to put the boundary points. They also count as local max or mins. So let's just plug into these points to find out which one is the highest, is the global maximum and global minimum. So if we plug in -2 into f of x, we get y is equal to -70. Okay? And if you plug in x is equal to 1, you get y is equal to 11. And if you plug in x is equal to 2, we get y is equal to 10. And when we plug in x is equal to 5, we get y is equal to 91. Okay, so I already did this all beforehand, so it might seem like I'm doing this really fast, but I already did the work out before this video. So the general idea is that when you have these values, you're looking at negative 70, 11, 10, and 91. Which one is the smallest value? Well, this is the smallest value, negative 70, right? Well, the negative 70 will tell us that since this is the smallest value, then negative 2 is got to be our global minimum. Or you could say it's our absolute minimum. Both ways work. So this would be our global minimum. Right? Now, which one is the biggest value? Well, it's 91, right? So since this is the biggest value, this can be referred to as our global max. And that's basically all you have to do. So if you ever want to find the max and mins of a equation, all you have to do is take the derivative and then find the zeros of those derivatives, right? Find the x-intercepts, and then you're gonna list them all out, right? Including the boundary points. So you have the negative 2, the 5, the 1, and the 2. And then you're gonna find the y values of each of those points. And then whatever is the smallest point is gonna be your global min, and whatever is your biggest point is gonna be your global max. So what about these other points, the 11 and the 10? Well, they're either gonna be local maxes or mins. Okay. So a general way to know which one's which is that if you kind of think about what the original equation looks like, right? So we have a cubic, right? So this is not the picture, but it generally looks like this, right? How a cubic works. Well, if you put them in order, right, we have a negative 2. This is not drawn to scale, obviously. So if this is like, let's say this is like negative 2. Let's say right here is negative 2, right? And let's say this is 1, and this is 2, and this is like 5 right here or something, right? So it's kind of not drawn to scale, so I'm not going to really put it at the exact point. So we have negative 2, so we have somewhere down here, right? Makes sense, right? Global min, right? Now we have a x is equal to 11, right? So somewhere here. Well, since I draw it a little bit off, this curve is supposed to be on top, right? So this curve was supposed to be x is equal 1. Sorry, so this is negative 2, and this is at 1. Sorry about that. So, see, this is why sometimes you don't want to put an axis, because then instead of writing an axis, you could just put in a parabola. I mean a cubic, something like this, right? And let's say, since you have to go in order, you just have to go from left to right, right? So negative 2. Negative 2 is like right here or something. And that's the global minimum, right? So it's the smallest point. Now, if we have x equal 1, so I'm right here, right? Then technically that is going to be our local max. So this is our local max right here. Okay. And now we have to go down. So this is at x is equal 1. This is at x is equal to negative 2, right? Let me redraw that. Negative 2. And this is at x is equal to 2, right? Because you're going from left to right, and you have to put them in order. So this will be our local min. Okay? And now you have, finally, x is equal to 5. So somewhere like right here. Then this is our global max. It doesn't look like our global max, but since we're not scaling really well, technically our x is equal to 5 is like somewhere over here where the parabola keeps going, right? So this will be our global max. Same for here, right? This doesn't look like negative 2, but negative 2 is like somewhere over here, which is our global min. I'm just using this as a reference. So if you pull out your like graphing calculator and see where these points lie, it gives you a better scaling of how it kind of looks. So general idea, if you want to find out if it's a local max or min, all you have to do is graph it out, do all this math, and then you kind of like think about the general idea of how the graph works. If it's a graph that you can't draw, then you could just trust the algebra because it makes sense. So, okay. Another thing is that if it's a global min, it's also a local min. If it's a global max, it's also a local max. So it could be two things at once. If you have a global max, you have a global. It's also a local max. If it's a global min, it's also a local min. However, if you have a local max, it's not a global max. Okay, so global could become local. A local cannot become global. Okay, so this has two names. It could be a local and a global. This could be a local, a global and a local, right? And this local cannot also be global, which makes sense, right? Because you can't have something that's local and then make it like bigger value because 91 is the biggest value, right? So that's all you have to think about. But it's just more for terminology than actually math. Okay, so that basically covers everything for max and mins. Let's move on to increasing and decreasing intervals. So increasing and decreasing intervals. So when you look at a derivative of a graph, if you see, the general idea is that if you look at the derivative of a graph, if you see anything below the x-axis, that means the original graph is increasing at that, if it's above the x-axis, it's increasing at that interval. And if you see anything below the x-axis, that means it's decreasing at that interval. Okay, so let's kind of use our same equation we did the previous example with max mins. So f of x is equal to our 2x to the power 3 minus our 9x squared plus our 12x plus our 6, right? And then that went from -2 to 5. So let's take a derivative of that, right? So when we're always working with these concepts with graphical aspects using calculus, we're going to be looking at the derivative or the second derivative, but that will be covered in the next video. So for this video, we'll just be working with the first derivative. So if we take the derivative of this, which we already did in a few seconds ago, a few minutes ago, so we have 6x squared minus 18x plus 12. And we had this as equal to 6x minus 1 and x minus 2, right? Okay. So all you have to do from this point is that you're going to make a sign chart. So we went from -2 to 5, right? So we're going to put everything in order. We have a -2, right? We have a 1, we have a 2, and we have a 5, right? These were our original points. Now we just got to put them all into like an order that, into a sign chart. So our order would technically go from -2 to 1, 1 to 2, oops, sorry about that, 1 to 2, and 2 to 5, right? So we have these three intervals that we have to check. So all we have to do is that we're just gonna plug in these points into our derivative. So if our points at the derivative is positive, then it's gotta be increasing at that interval. If it's the point is below that derivative, then it's gonna be decreasing. Okay, so let's kind of do this. And we have -2 and 1, right? So let's plug in something between them. Let's say 0, right? If we plug in 0 into 6 times x minus 1 times x minus 2, right? If we put in 0 into the x, we get -1 and we get -2. -1 times -2 is 2. 2 times 6 is 12. 12 is positive, right? So so this side, the first interval is positive. Since the interval is positive, it's also increasing. So it's not saying the derivative is increasing at that point. It's saying that the original function, f of x, not the derivative, which is the derivative of f, right? So if the derivative is positive, right, from -2 to 1 is positive, then that means f of x is increasing at -2 to 1. Okay, so let's do 1 and 2. If we plug in, like, let's say 1.5, right? If we plug in 1.5 in here, we get 1.5 minus 1, which is 0.5, and 1.5 minus 2, which is -0.5. So negative 0.5 times 0.5, that's negative 0.25, right? Negative 0.25 times 6 is negative 1.5. You really don't have to do the calculations. You just need to know if you're going to do negatives, if it's a negative or positive. I'm just doing it for you so you understand. So from 1 to 2, it's going to be negative. Since negative is below the x-axis, right? That means it's decreasing. Okay, now let's do 2 to 5. So let's choose a number between there. Let's say 3. If we plug in 3 into x minus 1, that gets 2. And if you put in 3 into x minus 2, we get 1. Right? So a positive times a positive times another positive is positive. Right? So since it's positive, that means it's increasing. Right? So if it's positive, it's increasing. If it's negative, it's decreasing. So what this tells us is that f of x is increasing at negative 2 and 1 to 1, and increasing also at 2 to 5. And the f of x is decreasing at 1 to 2. And that's all you had to do. And you could probably know that's true because a general idea for a cubic is, let me get out the axes so we can scale better. It looks like this, right? Well, it's increasing from here to up here, right? So that'll be negative 2 to 1, right? And then from 1 to 2, which is like somewhere here, all the way down here, is decreasing. And then from 2, which is here, all the way up here, right? It's got to be increasing. So the general idea also makes sense. And that's basically how you find it using derivatives. That basically covers everything for this video for maxes and mins and increasing and decreasing intervals. Thanks for watching, and I'll see you at the second part of part 7 of chapter 2.